So the title of my talk is Hausdorff moment problems for combinatorial numbers, heuristics via Meijer G function. And here is a list of my collaborators at various stages. Nick Baer, Kasia Górska, Duchamp, Maxim Kontsevich, Gleb Koshevoy, and Andrzej Chorzela, who is in Krakow on Zoom, I think. So that's why he's not on the list. I am going to talk, this is the plan of my talk. First of all, I will talk about subset of combinatorial numbers which are expressible through factorials or maybe gamma functions. But this subset is large enough, of course, but it doesn't contain all combinatorial functions. For instance, the famous Bell numbers are not expressible through factorials, and many functions concerning integer partitions are not in this subset. I will talk about the Hausdorff moment problem, which in fact means that I'm looking for integral representation of this combinatorial numbers, and I will study properties of solutions of the Hausdorff moment problem, and they include the solubility of the moment problem, positivity of solutions, and possible algebraicity of generating functions and solutions of the moment problem. And there are some guesses and even theorems about the relation of these three problems, but situation requires some more work. Then I will talk about eventual outlook. So what is the Hausdorff moment problem? This is a given set of numbers. We have to find a function which satisfies the following relation. It's nth moment of certain function, which is on the finite support. In our case, it's 0, r. Why, if we have a set of moments, why do you think that this representation is possible? One test is to form so-called ordinary generating function, where we take these moments, multiply by z to the end, and sum. And the test for convergence of this thing, which is called ordinary generating function, can be done by the Cauchy criterion, which says that this is converging if this limit, which contains moments, is smaller than infinity. And this limit turns to be the upper edge of the support. Okay? And the characterization of this moment problem is that if we get a solution, which is not even guaranteed, it is always unique. Now, some purists say that Hausdorff moment problem is obtaining positive solutions, but we will talk here about the cases that we obtain solutions which are not positive. Oh, this is question of terminology. So for me, the solutions of Hausdorff moment problem can be also a sign function. Well, it's just convention. So now it's important that we fix the the notation because no, I don't know why the first is not shown. Okay, so notation in this talk will be unified in the following sense. All moments are denoted by a row of n. Ordinary generating functions of all cases will be denoted by OGF of S of Z, and this will be also denoted G of Z. Weight function is W. This is because we want to avoid the proliferation of indices. We will have a large number of examples. Okay? So now the tools include the Mellin transform and its inverse. And this Mellin transform also encompasses so-called Meijer functions, which are defined as inverse Mellin transform. And the other tool, which is of different nature, is an online encyclopedia of integer sequences established by Sloan about 60 years ago. So now, just few words about Mellin transform. Mellin transform is defined for functions which are defined on positive half axis, and this is the definition. Here we have x to the power s minus 1 times function, and it's called Mellin transform parameterized by s. Now, inverse Mellin transform is acting on Mellin transform to get back the function f of x. This is an example which I would skip. And now I will introduce the very complicated structures which are called Meijer G functions. They are very complicated for just optical reasons, because hypergeometric functions contain two lists of parameters, and this creates some problems for some people already. This creature contains 4 lists of parameters, and they characterize the following thing. They characterize the product of ratios of certain gamma functions, okay? And inverse Mellin of certain products of gamma functions are called Mellin, Meijer G functions, okay? And well, you will understand through examples the role. So now there is one remark, that in all our applications for combinatorial numbers expressible through factorials, we always have only ratios of gamma function in the form s plus something, gamma s plus something in the denominator. So there are never cases of minus s. And this is extremely convenient, because the Meijer functions with factors which contain minus s are extremely unpleasant. So this is the situation. We always have these ratios. So now I will go to the simplest example of combinatorial function, which is central combinatorial numbers, which are central binomial coefficients. They are defined here, and then the symbols here enumerate or indicate the number of this sequence in Sloan basis. So you go to Sloan, you tape this number, and you get this sequence. Now, ordinary generating function of this sequence is a hypergeometric function in a very simple and known form. So the solution of the moment problem, which is here, can be done by considering the Mellin transform. How do we do that? We transform this symbol into gamma functions of s, where n is equal s minus 1. N is equal s minus 1 in all these things. And what we get a 1 ratio of gammas. And this Mellin transform is well known. This is sort of so-called beta functions, which are sometimes used. And it has the following very symmetric form. Here I plotted the solution of the moment problem for these central coefficients. And this solution is of the U form, very symmetric between 0 and 4. Because the support of this measure is 4. Why it is 4? Because the criterion, Cauchy criterion applied to this function gives exactly 4. Okay, and this is the analytical form of this distribution. It's singular on both edges of support, with a singularity x to minus 1/2. Why it is called arc-sinus distribution? Why? For purely historical reasons, because if you integrate this quantity from 0 to y, where y is smaller than 4, of course, this is so-called, how it is called? Sergey, you use this name. This cumulative distribution function, yes. You get just arc-sinus, okay? So that's why it is called. And it was, in fact, introduced by Paul Levy in 1939 and in the theory of stochastic processes, and treated by Paul Erdős in theory of numbers. And there are many, many applications of that. So this is a universal tool. So you can ask many questions about the continuation of this kind of examples. For instance, you can ask a question, do we know how to construct other moment problems which would have a slightly different form than this one? We want to retain the U-type shape, but we want to make it slightly asymmetric. So, for instance, the minimum would be not at the center of the support, okay? And I'll show you many examples where it is possible. So, first extension, which is very, very easy, is to say, I take binomial 2n over n, but I extend it by introducing integer here. So these are numbers also known by Sloan, and already this small extension gives a lot of novelty to the problem, because you can find a solution in terms of Meijer functions, but because here you will have two ratios of gamma functions. Two ratios. Here is a misprint. It should be m over 2. The solution is given here. I will not discuss solution. I will plot the curves. So one curve for m equals 0 is arc-sinus distribution. This is this olive curve. If you take m equals 1, the things already change, because here the singularity at 0 for the blue curve disappears. So this is one change. If we go to another change, namely we take larger values of m, 2 and 3, you will see that the function becomes negative. So the solutions of this simple extension of the central binomial distributions already become rather rich, and they transfer us from the positive solution into negative solutions. Okay. Well, it's what the remark about that is one thing which is rather funny, that this ordinary generating function is a product of the previous generating function times the mth product of Catalan generating function, which is well, unexpected, but not very deep. What I have to say is that all solutions of this extension of central binomial coefficients are solutions of the quadratic equation for the weight and for the ordinary generating function, which I have given before. And this does not depend on m. Here I took m equals 5 for two cases, and I get always second order algebraic equations. Well, now I come to the sequence which was suggested to us by Maxim Kontsevich, which has the following form, which is illustrated here. And now I will explain you in few words how do we get to the ratios of gammas. It is elementary, because we take the expression and we transform it into gamma functions, but we go to the variable s minus 1, and then you have gamma function 6, 3, multiplier 3, and 2 squared. Now we apply to this expression the Gauss-Legendre formula for multiplication of gamma functions, and we get here the ratios, 2 ratios of gamma functions, which should enter the Meijer function. And you see that the number of ratios has no relation with complexity of moments, because in the previous case we just took simple function, and we had 2 ratios of gamma. Now these moments here, are infinitely more complicated, but still there are 2 ratios of gamma functions which should serve for calculation. So the complexity with respect to gamma function is anti-intuitive. It is a result of unpleasant calculations. Now, what I want to stress is the set of parameters which serve to shift. Yes. Here we have ratio. The upper shifts are equal to minus 5, 6, minus 1, 6, and down shifts are equal to 0, minus 1/2. Now, I give here a partial answer to the question which I asked, namely, can we reproduce U-shaped positive functions which are not symmetric with respect to the half of the support, and they have different singularity? And the answer is yes, because the solution of moment problem for this Kontsevich sequence has U-type shape. It is positive, but the minimum is not at the half of the support. And now I will now proceed to produce the algebraic functions which are obtained by the solutions. So the solution for weight function is given by the inverse Mellin transform of these 2 gamma ratios. And this can be done, and happily enough, this is a simple, I would say, elementary function, expressible through radicals. And we can find solutions for algebraic function related to this W, which is of 6th order. But I will explain you that, in fact, it is for 3rd order by some rescaling, which was suggested by Kontsevich. Now, algebraic equation of generating function is also of 6th order, and apparently they can be related. These 2 algebraic equations can be related. I go now to next example. Next example is very close to this previous example. I will explain you why. Because this is a binomial 3n over n. And the solution for the moment problem is again sort of elementary function. It means it can be expressed through the square roots and so on. This is the solution. Now, generating function for this moment, it's written here. And well, it also can be expressed through elementary functions. And now, again, algebraic equations are of 6th order and for W, and of 3rd order for generating function. And again, now you can do sort of rescaling of the variable and define a new variable y for which we have equation of third order. Now I will quote, I will now plot the solution here, and you see it's again not symmetric with respect to the half of the support, and it is given by this number. But now I will quote one finding, which we call maybe a theorem, because it's exact. Namely, we, for certain solutions of moment problem, we find the order of algebraic equations. But we don't find the given, we don't have a formula for an algebraic equation. We cannot reproduce the numbers in this equation. With two exceptions, which I will tell you, because these moments have algebraic equation of order p. So this p is equal to 3, and for general p, I can write down algebraic equation of order p for generating function. Okay, and this is an exact result. For p equals 3, we get exactly this equation, and for order 4 and 5 and so on, this is an exact result. Okay, so not only we have an order, which is probably also exact, but we have exact form of algebraic equation. So now I'll go to another series of moments, which are this time a little bit more unpleasant. Why I have chosen binomial 3n minus 1 over n? Because we can observe that the generating function for this moment is not a single hypergeometric function. It is a slightly modified expression which contains z and so on. And this has some bearing on the things which I will tell you in 5 minutes. But nevertheless, although this is a strange generating function, it still satisfies a very nice equation of this kind for the generating function. And also there is an equation for w, which is also obtained, which I don't quote again. Now, this kind of moment, along with the previous moments of type Pn, type Pn over n, allow here once again a closed formula for the generating function, which is again of order p. So if you have Pn minus 1 over n, your generating function satisfies another algebraic equation, which is given by exact formula. And well, you can play with that. So for instance, for 4n minus 1 over n, this algebraic equation is of fourth order, but it's exact. Okay, so you see now that there is a certain regularity. Now you can ask me whether other form of moments like 3n minus 2 over n, do they have exact expression for algebraic equations? And the answer is, I don't know. For some reasons which are hidden in some calculational details, you cannot give this kind of equations for other cases up to now. Okay. Now I go now to the next example, which is the series 3n plus 2. Before we had 3n, now I do 3n plus 2. This is also nice thing. Again, you can now introduce a new variable, which is called y, and it contains the 6th power of w. And this function satisfies the cubic equation along with the cubic equation which is satisfied by generating function. Now, this kind of consideration were initiated by Maxim Kontsevich last year in his talk here in this conference, where he did the very simple rescaling for his previous case of this kind of moments. And you see there is a difference. Here is w square, here is w6. Well, it is like that, because essentially equation is of order 18. So in order to get the cubic equation, you have to rescale it through this kind of equation.
Excuse me, these equations have no explicit
No. The only explicit form are for Pn over n and Pn minus 1 over n.
Yeah.
I don't know why, at least to my knowledge. I don't say that somebody will. Okay, so now for 3n plus 2, we obtain again the explicit and elementary expression for the weight function. But you see that this weight function has a different form. It is an exact solution for the moment problem, but it's not anymore singular at 0. Well, that happens. So we somehow quit the series of U-shaped functions, and now I can tell you, if you go to example which will be 3n plus 3, then the function will not be any more positive. So this is sort of parametrization which brings us from the positive solutions to sign solutions. It's a sort of observation. Okay, now now I go to the much more complicated example, because this is binomial 5n over 2n. So now if you look at the generating function, it's a function for hypergeometric function of type 4, 3. Now the support is here. I don't remember what is the value, anyhow, maybe in the next. Now, what is important? This is the first case in this presentation where we have 4 gamma ratios. Okay, so 4 gamma ratios for this moment. Now, if I look closely at these ratios, I can state the this is the support. It's here around 29. If I look at this structure, I see that the generating function is a single hypergeometric function. Now, if I look at the Mellin transform inverse of these 4 ratios, I will get something. Maybe we'll look at this thing. I will get something which again has this U-shaped form. It is not symmetric. This is a ratio, but nevertheless, I want to now point out a certain observation, which we already done for other examples, but now it's a good point to make it. Namely, if I look at the previous thing, I see the numbers which are, first of all, lists of hypergeometric function which is which is generating function. So there are two lists here. And I look at the gamma shifts here and here. And what can I say? That if I look with a bare eye, I see that the gamma shifts are just a negative of this list of parameters, upper. Now, if I look at the gamma shifts here downstairs, I see there are just negative of the second list, with one exception, that there is a no shift here added to that to make 4 gamma shifts. So there is a 0 shift, and there are negative shifts with respect to the parameters of generating function. So this brings us to a heuristic observation, once again, that maybe the Mellin transform to get a weight function is not needed, because there is some regularity that in order to get Mellin transform, you have to shift the lists of parameters between some functions, and that you get something which satisfies our problem, because we first done Mellin transform, and then we see that just it's enough to shift. What is going to be shifted? We look at the following structure, but this is without proof. This is just observation. That if I take generating function and I write it in Meijer function notation, then I get two lists, L1, L2, and my argument is minus z over r. Don't ask me why, because are properties of Meijer function. I have no time to explain. But then I look at the weight function solution by Mellin transform. What happens? I take this 0, which I move from one list of parameters to other list of parameters. Here I say the argument is x over support, and I get my solution of the Hausdorff moment problem. Okay? Now, there is one problem, namely, here we have proportionality signs. So there are some numbers which are involved. I have no time to explain you now, but we know how to extract the necessary numbers. As you suspect, these numbers must be somehow related to this to these lists. Okay? There are two lists. For instance, here in this case, just previous case, it doesn't move. Okay, well, I have it here. So I hope. Okay, so you see, you change the sign, and you put these things in new brackets, and you add 0. Okay, and this is a recipe, and which is, let's say, experimentally observed. So now, how much time do I get?
Yes. Well, 10 minutes, 9 minutes.
5 minutes?
9.
9. Okay. Well, doesn't react.
Non, mais c'est pour passer la slide à la suivante.
Yes.
Yes, you must click.
Okay. Okay. So now, of course, so as you see, there's a weight function here, once again, here, and I said it's obtained by moving 0 from one list of parameters to another one. It is very practical, because otherwise the obtention of weight functions is very complicated. It's a very nasty function, which I show you. Oh no, I don't know why. Okay, this is now a solution for the previous example. It contains, if I see correctly, 5 hypergeometric functions. So it's extremely difficult to operate with such things. I will not bother how to do. But anyhow, this prescription, which I pointed out here, has been checked on an enormous amount of examples. Enormous amount. And I will show you what are the examples. Okay, the examples contain the expressions for moments which were obtained by Jonathan Bober in his paper, in which he found the structure of certain moments which allow for algebraicity of their algebraic functions, generating functions. Okay, so these are here examples of 3 series which are parameterized by integers a and b, which are mutually prime numbers. First example, which is related to binomial expressions for moments, as you see. There is a second series, and the series of the example of Kontsevich is a member of this series, and there is a third series, which are all of them parameterized. Now there are also 52 non-parameterized cases, and an example of this non-parameterized case is here. They are called sporadic moments, sporadic series of moments, and we, with our method of Mellin transform, and also with the method of shifting 0 from one list of parameters to another list, we have obtained and checked this relation. And this relation I quote now for this sequence, which is a member of third series of Bober, 2009, and well, this has again this U-type shape of the weight function, and we obtained also the explicit algebraic equation of 10th degree. Okay, and this has this number by Sloan, 4, 6, 2, 3, 5 factorials. Okay, so this is perfectly checked. Now I come to the last example, which is a famous Chebyshev sequence, which has this horrible formula. I'm sorry, these are very small letterings. I was unable to increase the size. Anyhow, it has a generating function which is f 8, 7, I believe, and the solution of the weight is Meijer function, which is obtained from the Meijer representation of hypergeometric function with added 0. Okay, and Chebyshev sequence has this number, and it is one of sporadic Bober cases. So the solution was obtained, and this satisfies this rule which I have exposed. And the last thing I will just sketch is that we considered some other sequences of moments. Some of them were dug out because they were not used for many years. These are so-called Tutte numbers with m is positive integer, and they have this formula. It's not very complicated because it contains 4n factorial, 3n factorial, n factorial with some shifts. And we obtained solution, exact solution of this for these moments, and they belong to the category where positivity disappears when m is larger than 2, I believe. Larger equals 2. So solutions are obtained. They are positive for m equals 0 and 1, and negative. And they were obtained through this scheme which I've here was talking about. The second series, and last I will mention now, are so-called number of intervals on M Tamari lattices. Okay, it's a horrible name, but it describes some complicated combinatorial constructs which can be enumerated by this formula. It's very fashionable nowadays. 30 seconds, I'm finished. It's very much practiced by Noam Zeilberger, Vienno, Eric Fussy, Gilles Schaeffer, and so on. And we have solutions, exact solutions for everything, including the order of generating function, which is equal here to m plus 1 square. And these are numerical results, not exact, maybe. Well, there are other things which fit to the scheme. So the last sentence is that there is a regularity for this kind of moments which reduces the work investment needed to solve these problems, because it's just a sort of algorithm. We don't know whether this is exact, and we have several counterexamples. And the necessary condition to our mind is that the generating function for moments must be a single hypergeometric function. Once they are, for instance, 2, it doesn't work.
So questions? Yes?
So at some time, I believe that you asked about the algebraic nature of the corresponding hypergeometric function. And to what extent, there is this work by Bulkers and Ekman, I believe,
Yes.
which is doing, I think, a full classification of the algebraic.
Exactly, yes.
So which cases are still open, or why were you asking for this algebraic?
First of all, first motivation is to solve the moment problem for these things which probably satisfy the conditions for Bulkers and Ekman. Okay, so because they just considered generating function, we have also weight function. Okay, we couldn't for this, for instance, exotic sequences like that, we couldn't really verify whether they fall into category of Beckmann, Bulkers and Beckmann, but probably they will do. But the difficulty that we have is that in the work of Bulkers Ekman, the parameters are always smaller than 1. All lists are smaller than 1. If you look at, for instance, intervals of M Tamari lattices, the lists of parameters in generating functions contain, large numbers. If M is large, of course, there are conditions of modulo something. Yeah, but this is difficult to verify, at least for me.
Other questions? Remarks? Let us thank the speaker again.